Final speaker tonight is our Changemaker, Saadia Wasim, a PhD student in the Department of Civil Engineering working under the supervision of Professor Stephanie Loeb. Saadia is going to tell us the story of how rays of sunshine can be the hope to clean our drinking water sources.
Water is essential for life. Personally, I like to look at water differently. Or should I say, I like to taste every sip I consume, feeling how heavy or light it is to my throat. 9 weeks ago, when I was breaking my fast with some dates and water, as I was drinking the water, I recalled this newspaper interview which I had read around my high school days. It was about a couple who were traveling through the desert and had exhausted all their water supplies. So basically, they were thirsty and tired. Luckily, they found a house and went for some help. The owners of the house, just like any other Bedouins, served them with some dates and water. That water was a memorable one for them. They clearly remembered how drinking that water made them feel. And so, 4 decades later, when they were being interviewed by that local newspaper, they narrated this water story. I completely resonated with these couples when I was drinking that water while breaking my fast. Also, it would be nice if this could happen today in today's world, like people would travel in resource-limited regions and be served water which they could drink, not fearing how bad it is or good it is. The unfortunate reality is our water bodies today have been contaminated with toxic chemicals and microorganisms. Fortunately, these toxic chemicals and microorganisms get removed by these large-scale water treatment facilities in developed or urban regions. And thanks to these large-scale water treatment facilities, 6 billion people globally have access to safe and clean water supplies. But knowing that the global population is 8 billion, there are still 2 billion people who lack access to safe and clean water. These 2 billion people live in regions marked by yellow and orange. So now the good question is, how do we help these remaining 2 billion people or these regions gain access to safe and clean water supplies? Those large-scale water treatment plants is not a sustainable option for these regions as they lack those resources. A closer look into these regions shows us that they are located near equator, which means they have sunlight or solar energy all year round. We can use this as an alternate source of energy. Moreover, people in these regions live in small communities like these, and so an ideal solution would be more of a small-scale decentralized unit. Again, in developed regions, water gets treated, that is, chemical contaminants are removed from water using filtration process, which can be energy intensive, and microorganisms are killed or disinfection is carried out using processes like chlorination, UV disinfection, ozonation, and so on. And these have their own drawbacks. I propose the use of sunlight-driven process or solar-driven process for these resource-limited regions. By using sunlight, I don't mean to produce electricity, but to use them directly to degrade contaminants and kill microorganisms in water. Now you may be wondering, how would that really happen? Well, if we use nanoparticles called photocatalysts. So photocatalysts are nanoparticles that have the special ability of getting activated by light energy to degrade contaminants and kill microorganisms in water. To elaborate more, these photocatalysts have a conduction band and a valence band, and once a photon of sufficient energy is absorbed by these photocatalysts, electrons get excited from the valence band into the conduction band. These excited electrons in holes or positive charge then move on to the surface to perform surface reaction. During this process, they generate these short-lived chemical species which have the super ability to degrade contaminants and kill microorganisms in water, breaking them down into safer byproducts. The photocatalyst of my interest is traditionally used using UV light sources, but I want to use sunlight, and they don't really work that well under sunlight. Why? Well, because sunlight contains less than 4% of UV region, which only gets absorbed by these photocatalysts. Here's a sunlight spectrum that reaches the Earth's surface. That is the sunlight that reaches the Earth's surface. On the x-axis, we have wavelength, which you can think of as different regions in the sunlight that reaches the Earth's surface. That is UV, ultraviolet, visible, that is visible to our eyes, and infrared, IR. So these 3 regions are found on the Earth's surface. On the y-axis, we have intensity. That is, how intense is light in each of these regions. So on the extreme left, you can clearly see that UV has the shortest or the smallest portion and the lowest intensity amongst the three regions. And that makes sense why these photocatalysts don't really work that well under sunlight. So the challenge for me was to improve their performance under sunlight. And I approached that by using another nanoparticle called plasmonic nanoparticles. I would like to call them as light antenna nanoparticles for this presentation. These light antenna nanoparticles have this special ability to concentrate light energy on their surface, and this kind of a phenomena does not happen for a photocatalyst. So the thought was, what would happen if we couple these two nanoparticles together? So for demonstration purpose, light rays would concentrate on the surface of the plasmonic or the light antenna nanoparticles, and this would happen for each of the light antenna nanoparticles. This concentrated light energy would then be transferred to the photocatalyst and then help it improve its performance. The light antenna nanoparticles of my interest is aluminum nanoparticles. These were synthesized using a special fume hood setup called Schlenk line. In order for the reaction to begin, the reactor was first placed under inert vacuum followed by an inert environment. Once the reactor was in inert environment, chemicals were added to start the reaction and eventually wind up the reaction. Once the reaction was complete, these nanoparticles were washed and analyzed to check if we have synthesized the desired nanoparticles. Here's the analysis results. You see an image which shows nanoparticles, small balls with two different colors. The core is red, which is aluminum, and there's a thin sheet of oxygen, which is the oxide shell, and this is what I wanted. So this confirms the successful synthesis of my aluminum nanoparticles. Now that I had my aluminum nanoparticles ready, the next step was to attach them or couple them with the photocatalyst. I thought to myself, why not place the photocatalyst in the reactor itself and let the aluminum nanoparticles deposit on top of it, which is an option. But that was not the best thought. That resulted in over-deposition or aggregation of aluminum nanoparticles around the surface of the photocatalyst. This decreased the performance of the photocatalyst, which is not what we wanted. So the only way to overcome this challenge for me was to synthesize the aluminum nanoparticles separately and then attach them to the photocatalyst in a controlled manner. And to do that, I use something called ligands. You can think of ligands as a network between two nodes. So I used different types of ligands with two different attaching groups. That is represented by squares and circles. So I had square and circle, 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 and square. I found that the one with the square and circle performed the best. Next, I thought to myself, if I keep the attachment group constant, what would happen if I vary the length of these ligands? And I found that the shortest one performed the best. So this was a constant for the next round of experiments. And now the big moment. The results for the degradation of a selected contaminant under sunlight using those nanoparticles. On the y-axis, we have percentage of degradation, and it's supposed to increase from left to right. And on the x-axis, we have the time needed for these contaminants to degrade. So first off, we have a control, which is the photocatalyst, and here's how the degradation curve looks like. Next, we have another control, which is the ligand with the photocatalyst, and that's another control. So this is how the degradation curve looks like. In this, we see that these ligands did not impact the degradation performance. That is, it did not increase or decrease the degradation performance. And finally, the hero of my project, the light antenna ligand and the photocatalyst, here's the degradation curve. We clearly see an enhancement in the degradation performance, and this is about 60%. This can solely be attributed to these light antenna nanoparticles, meaning that these light antenna nanoparticles were successful in concentrating the light energy and then transferring it to the photocatalyst. This was a test run performed for 20 minutes. Now I'm trying to see how long would it take me to degrade these contaminants completely. Another important question that I'm trying to answer is this enhancement because we are absorbing more of UV light or we are absorbing more than UV light? Either ways, with such an enhanced performance, these photocatalysts or these nanoparticles can be coated on sunlight transparent substrates, which can then be used in these solar powered small scale water purification systems. So what happens is light penetrates through the sunlight transparent substrate, activates the particles. These particles can then go on to degrade contaminants and kill microorganisms in the water flowing through the channels below the substrate. These solar powered water purification systems can be used in those communities that have sunlight throughout the year. I too come from a country that has sunlight throughout the year. Summer mornings can be as hot as 45 degrees Celsius, and that is really, really, really hot. You can crack an egg and cook it on the floor. When I started my PhD here at McGill, I was drawn to the concept of using light for water treatment. Maybe because sunlight was a crucial part of my life. But little did I know that sunlight would actually become the theme of my thesis. The results that I presented today were an accidental exploration. They were not the main experiments I was conducting. While I was doing my main experiments, I thought to myself, why not use the solar simulator, which is basically a light source that mimics the sunlight that reaches the Earth's surface. The results we got were interestingly amazing, just like what we saw today. When I talk about my own work, I feel incredibly blessed that I'm able to share my appreciation for both light and water with you today. And most importantly, bring water to a part of the world that is hesitant about it. Hopefully with this kind of a system, we'll be able to provide safe and clean water to the remaining 2 billion people. Thank you.